All right, so this is truly a new topic, but I think you will be able to grasp it very fast, as that's my impression, right? So what you do is this. We are not always interested in the original sample space. As in, for example, have you watched the movie Deer Hunter? Do you know this movie? It's a pretty good movie, not new, with what's the other guy? Not Al Pacino, but Robert De Niro. That's right, with Robert De Niro and I cannot ever remember names of actors, but good actors. I think Chris Walken is the other one, right? And it's called Deer Hunter. And then they depict the Vietnam War, and they show forced Russian roulette, for example. So when you play a Russian roulette, you can imagine that the universe is narrowed down to seven possible outcomes. So I can consider S, the sample space, as the super universe, or the universe of possibilities, and the possibilities are state 1, state 2, 3, 4, 5, etc. Maybe in only the first chamber you have the bullet. So you don't really care that each individual outcome occurs. What you do care is whether the pistol fires or not. So your sample space of interest is the sample space S star, which is bullet fired or bullet not fired. Yes? And the way this game is played, of course, is that if you do it once, you just roll the drum and then you press the trigger, right? So each outcome seems to be equally likely to occur, right? But outcome number 1 is collapsed to bullet fired. The other outcomes are collapsed to bullet not fired. So collapsing those outcomes naturally, you see, what we do is we call this a function X. So this X is going to be called random variable. But really, there is nothing random about the X itself. It's just a function from S onto another S star. And then it will induce another sample space S star, where you can imagine that each of those outcomes are like stones or small pebbles. And they have, in this case, identical weights. And what you do is whenever several pebbles are mapped into the same event, it's like you are melting them together into a bigger pebble, and they keep the weights. So you see, so N weighs the sum of those weights. It's 6 weights, each of them 1/7, right? So what you do have here is now a sample space with 2 possibilities, which is like an unfair coin, a biased coin that comes out, I don't know if you call it tails, with probability 6/7 and heads with probability 1/7. Okay, so that's what random variables are. Nothing more than just a function that is from one sample space onto another set, and it makes the other set an induced sample space. So far makes sense? So here I make this definition. X is from S onto S prime, or sorry, S star, and it has to be a surjective map. And then X induces a probability on the set S star and makes it into a sample space. And how do you calculate the probability? Simply consider any event Y in the sample space S star. So for example, consider this as my Y. I just retrace what it was made out of, and I add the probabilities that correspond to it, right? So N was made out of those outcomes, and I just add up the probabilities corresponding to them. Make sense? Wonderful. So here I just show what it is. So that's what I say X inverse. It just means trace all the inputs that made Y, and then add up their probabilities. Well, that's what this is saying. Yes. And here is a very easy example. 3 balls randomly selected without replacement, and the urn contains 20 balls numbered 1 through 20. If we bet that at least one chosen ball has the number as large as 17, then what's the probability that we win the bet? So you see, we don't really need random variables for this problem, but we might as well list the interesting outcomes in terms of largest value chosen. So X picks, it's a function. You see, when I say X equal, I'm suppressing what it truly did. So X is just a function that, let's say, picked the outcomes. Maybe the balls that came out are 1, 2, and 3. And it tells me that the biggest was 3. It gives me maximum of the 3 particular occurrences that took place, right? 2 particular samples. Good? Makes sense, right? So then if I want to know how likely I am to win this game, I will ask for probability where X is bigger than 17. And that means either X is 17 or x is 18, or x is 19, or x is 20. That means the largest value selected is 17, 18, 19, or 20. Now, for each of them, it's easy to calculate the probabilities. If 17 is the largest, I have another 2 out of 16, right? So because they can, none of them can exceed 17. So it's 16 choose 2, plus 17 choose 2, plus 18 choose 2, plus 19 choose 2. Why 19? Because 20 is the biggest one, right? And divided by the probability of just also the probability of all possibilities of choosing 3 out of 20. Yes, 20 choose 3, 0.508. Slightly over 1/2 is my probability of winning the bet. Make sense so far? Yeah, great. So when I first learned it, you know, the name random variable, many names are somewhat confusing, right? So there is nothing random about it. It's just a conversion from one sample space to another. So here is an example. Suppose a fair die is tossed until it comes up 6. And x denotes the number of tosses required. So clearly the number of tosses required will be either 1 or 2 or 3 or some integer n, or possibly it will take infinitely many tosses. In other words, somehow I roll and roll and roll and roll and roll and never ever observe 6 coming out on the die. I just included here as maybe you cannot even imagine this possibility of being anything meaningful, but who knows, right? Maybe it just you roll it forever until the end of the universe and nothing happens. So the probability that x equal 1 is 1 over 6. When I say x equal 1, I suppress what happened here. X, so the sample space here looks something like this, right? So x equal 1 means that x of something happened on the first trial that was not a 6, and it ended up in a 6. So box means either 1 or 2 or 3 or 4 or 5, and 6 it is the end of the game, right? So probability that it took, sorry, not this box. It should be actually just 6 first. Yes, maybe that's what you wanted to tell me. Okay, log out and log back in when you need to. So again, back to the idea. The probability that x equals to 1, what am I truly saying? Probability x equal 1, it means that on the first trial I was successful, right? So it's really, it means x of 6, right? And I ask for the probability of that, right? X of 6, just one event is collapsed. The probability is clearly 1 out of 6. Agreed? Now probability x equal to 2, it's really the probability of x given that the outcome was something, but that's not 6, and 6. That's really what happened here, yes? Something and not 6, and so something and not 6, the probability of that is 5 over 6 times 1 over 6. And so on, yes? So in general, probability that x equals to n, in other words, that n trials were required, means that we had n-1 failures and 1 success at the end, right? So it's 5 over 6 to the n-1 times 1 over 6. And you can see that the bigger the n, the less is the probability. So they don't, each of the nodes in my sample space don't weigh the same amount. The pebbles are not as, so beginning pebbles are heavier than the pebbles at the end. They decrease in weight. And so now let's calculate the probability that I will have to wait finitely many steps. So that's what this means, right? X is an n, means that I will see a 6 after some integer. So I either see 6 on first integer or second or third and all the way to onwards to infinity. This probability is that of 5 over 6 to the n-1 times 1 over 6. And the way we sum geometric series, it's like 1 over 1 minus the radius of a geometric series times the constant 1 over 6 here. You know it, right? I don't need to review this part, right? So it's all immediate. If yes, then I'll review it again, right? So this is then probability equal to 1, which means that probability that x equals to infinity is 1 minus the probability that x does not equal infinity, that it's a finite integer, and that will be 0. Yes? So then I ask a rather silly question. Does it mean, of course, does it mean that infinity cannot happen?
I would say no, just because, I mean, I guess in some universe you could roll the dice forever and never get a 6. It's just very, 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 very unlikely.
Yeah, so it's really in some sense in our universe a meaningless question, right? First of all, I will never roll the die infinitely many times, right? So if somehow I could do it in a finite amount, somehow I just roll it and it's like I'm not sure, some sort of crazy quantum mechanical who knows what. Somehow it's as if I rolled it infinitely many times. And will I ever observe a 6? The answer is that it is. If I observe a 6, I'll probably never observe it again, right? And practically speaking, you will never observe a 6. So practically speaking, because you see, when you do it finitely many times and you see an observation, you see this observation, that makes it already unlikely that the probability is 0. Even though, remember, when you order a delivery, that always happens, right? Your delivery person, if you could, again, if it's meaningful to divide time forever, your delivery person arrives at some moment that will never ever repeat. If you play the experiment again, the same moment never repeats. So it's a miracle every time a delivery person gives you something, right? Brings you something. Right? So miracles happen. So now we talk about discrete random variables. So those are random variables. Have you taken analysis before? You know what's countably many. So either a discrete random variable is either a random variable that has finitely many outputs or infinitely many outputs, but those that can be matched in one-to-one correspondence with the positive integers, right? So I can list them, 1, 2, 3. It's like a Soviet numbers. It means that you can stand in a queue line for smelly fish, for example, right? Because that's all you are going to get, or dead blue chicken. Soon people will know what it means if, of course, somebody gets elected. Sorry for my silly jokes. So the probabilities, of course, must add up to 1. Yeah, so the probabilities of all those possible outputs, because we have the new sample space is that of those payoffs or those outputs, it must add up to 1. Yes, and here is a simple example. So if I toss a fair coin twice, then I might want to know how many times did I get heads. So either I got it 0 times or 1 or 2 times, right? And then probability of 0, that's my finite value, it's 1/4. Of 1, it's 1/2. Of 2, it's 1/4 as well. And I drew it like this, even though in practice, there is no reason to have such a wide, thick box here, right? It's possibly nicer and better represented to draw it like this. Yeah, because the length of the stick will be then 1/4, this 1/2, and this 2, because only 0 or 1 or 2 can occur. Good. So here is this is called, by the way, did I mention it's called probability mass function? Mass because it's like the mass of the particle, right? So it's like a stone. Each outcome is like a stone, like what we had over here. Each of those outcomes is like one small stone. In this case, they weigh the same amount. Here, this is a heavier stone because smaller stones were collapsed together, and that's its weight. So that's why we call in the sample space the actual nodes that have non-zero probability, we call them masses, and then with the probability mass function, it's just a function that assigns all the numbers a value between 0 and 1. Most of the values will be assigned 0, of course, and those that are assigned non-zero value, right? Those are the ones that can actually well, that actually make any interesting sense. So the function that assigns the weights is called a probability mass function. So in this case, 0 is assigned the weight of 1/4, 1 is assigned the weight of 1/2, and 2 is assigned the weight of 1/4. Right? So here is this question. The probability mass function of a random variable x is given by Pn, c times lambda to the n over n factorial. Lambda here is assumed to be known. If you want to, you can imagine lambda equals to 2. Right? So could you possibly tell me what is the value of c, and then calculate probability that x equals 0 in terms of lambda, right?
Hold on. So I have to give you the value of c?
Yes, if you can, of course.
Wouldn't it? Hold on. I have to reread the question. Sorry.
No trouble.
Probability matching for random variable x. Okay. Oh, I see it because a. Okay, sorry. Not sure exactly what you would do.
Well, but what should all the weights add up to?
1.
Exactly. Here you go. So you add it up, right? And then you figure out what must c equal to.
Oh, so c it's also 1?
No, because you see, look at it. You add it up. Actually, I have it written over here, right here.
Yeah.
1 is equal to the summation from n equals 0 to infinity, because you see the probability, the non-zero weights must add up to 1. Do you agree? The probability mass function must add up to 1, because it's certain in the sample space that one of the outcomes will take place. That's the idea, right? So a sample space must include the set of all possible outcomes, right? So the sum of the non-zero weights, non-zero probabilities, has to add up to 1. So what is the summation? It's c times lambda n over n factorial. I can factor out c and then look at the summation. The summation looks like it's the Taylor expansion or infinite series expansion for e to the lambda. Do you agree? And do you need do I need to mention what's Taylor series?
No, I think I get it. And then yeah. I just have to haven't done Taylor series in a while, so it doesn't come.
Well, in my review though, we have a review, remember? So if you want, we can go over that, no trouble, right? So it's a very simple idea. It's just e to the x. How do you calculate using e to the x? What is that truly doing? So the only calculations we understand: multiplication and addition. And then you think, you see, it's really somewhat. What is e to the x? E to the x. It's a really meaningless expression. Maybe even if I know the number e, I might understand what is e cubed, which is e times e times e, yes? But what is, let's say, e to the power of pi? What does that mean, right? So the fact that it's written in the power, it makes it not more understandable. It's truly a function whose derivative is equal to 0, and at 0 it's equal to 1. And then you figure out what sort of function could that be. Could it be a polynomial, right? Well, polynomials after many derivatives disappear to 0. Make sense? So then you say, if you imagine, well, maybe then it's an infinite polynomial, because you really like polynomials. Polynomials are easy. It's just addition and multiplication. That's all you're doing. Make sense? Yes. So then you imagine it's an infinite polynomial, and you find the coefficients. So it's like you know, anything like it's any function f of x that's an infinite polynomial might have coefficients a0 plus a1x plus a2x squared and onward, right? So then how do you find a0? You just plug in 0. How do you find a1? You take the derivative, and then a1 is in the position where there is no x. And then doing that again, you get a Taylor series. That's as simple as that. So the fact that you call it Taylor series, and perhaps the procedure is not, the procedure is just elementary. It's just an infinite polynomial, and you're detecting the coefficients. Make sense? So that was just very quick, but hopefully refreshes your mind, right? One moment, you can hear the cat screaming, can you? Do you want to see them or not so much? Or I'll toss them out of the room.
Sure.
Okay.
I like cats or any pet.
Yeah, so this is one. He almost scratched my eye out yesterday. Very close to it. It's not seen, but he injected his claws right in here.
Oh no.
All right, and that's what happens when I become angry. It becomes a black cat.
I see.
Yeah. As I threw him out, the other cat bit him in the neck. That's how it goes. So, yes. Anyhow, sorry for the distraction. They just scream around. The black cat can open doors now. So now the doors are with a round handle, so you would not be able to do it. Yeah. So what you have is then c times e to the lambda is 1. So all you have to do divide by e to the lambda, which is c then, right? So c equals to e to the minus lambda. Make sense? And now what's the probability that x equals to 0? It's simply the weight, the mass, right, of 0, which is e to the minus lambda, lambda to the 0 over 0 factorial, or simply e to the minus lambda. It's going to be later, we will see much more about it. It's the Poisson random variable, very important random variable, right? But right now it's just showing what weights are. And then the probability that x is bigger than 2 is simply 1 minus probability that x is less than or equal to 2, which is 1 minus the probabilities of x0, x1, and x2. And here they are, right? I just plug into my mass function. I can forget what it's called always. Into the mass function, I plug in the value 0, 1, and 2. And I get this expression. Nothing so strange, yes? Good. Now, cumulative distribution, just it's somewhat wedged here, perhaps unnecessarily. But let's try to go over it. It's going to be important for chapter 5, especially. So a discrete random variable has this cumulative distribution function, which what you do is that the random variable takes, let's say, real numbers. And what you do is select the number a, and the cumulative distribution are all the pebbles that will be picked that are equal to a or less than a, right? So all the masses that are, so it will look something like this, right? So imagine that we have this distribution and we have certain masses here. So those sticks that are coming out of the x-axis are all the places where probability isn't 0. And then somewhere over here, I select A, and so it sweeps and adds up all the sticks together. It adds them up. That's what this is about, right? That's what the summation is indicating. Add up all the weights of pebbles that are located to the left of A, or possibly at A. Good. So here is an example. So if x has probability mass function that at 1 it's 1/4, at 2 it's 1/2, at 3 it's 1/8, at 4 it's 1/8 as well. And then the cumulative distribution is 0 for all a smaller than 1, because to the left of 1 I pick nothing at all, right? And then if I am smaller than 2 but bigger than or equal to 1, I pick the one pebble 1, and therefore I add up its weight, 1/4. Now if I am farther, if I am between 2 and 3, and then I pick the weight of 2 and the weight of 1, which is 1/4 plus 1/2. And if I'm further between 3 and 4, I pick the extra weight of 3. And finally, if I am more than 4, then I pick up all the weights. It's going to be 1, right? So the way the distribution looks is like in this drawing. Make sense? It's a step function. Now you can see that A, as I move, so A is this. As I sweep my everything to the left of this point, of this shining point, then I'm not picking any weights. I'm not picking any weight. Suddenly, as soon as I jump over at 1 or over 1, I pick this weight. Right? So that's what is indicated. Now here, nothing else is picked because the weight that I sweep is still just that of 1, that of 1, that of 1. And then again, there is a jump because as soon as I'm at 2, I picked another weight. So it's a function that's right continuous, you see, but not left continuous in this case. As I move onwards, I pick up the weights until after 4, I'm just not picking anything more. It's just steady at 1. Okay, so I'm not sure, right? In my limited experience, I do not know what's the point of cumulative distributions in discrete random variables, but I definitely see the point when you have continuous random variables. So that's why I'm saying that I shoved it somewhere here. I'm not sure if there is too much benefit in it at the moment. Now, this is a very important topic, expected value. What happens if we play a game of chance habitually? So for example, you order a lottery ticket. Let's say you can win $1 million, but the lottery ticket costs 1, right? And that's the problem, that it's hard for me to say, is it a good idea to play it once or not, right? Or you play it once, you might say, aha, I win $1 million, and you mentioning that it's not a good idea to gamble was a stupid idea because I won $1 million. I had feeling in my stomach of sorts, right? Maybe it's hard for me to truly, even at this point, to tell you if playing one game is a good idea or not, but I can definitely say that if you play many games, then it's a very bad idea. The more games you play, the worse is the idea, because prediction becomes very regular once you repeat something many times. One time you can be lucky, many times you will not be lucky. So the idea is, let's say I did it abstractly and many people fail to understand. I had to go back and forth. I have an example of it, right? So if a game of chance has different outcomes, different payoffs, it could be positive or negative, and those payoffs are x1, x2, x3, x4, x5 onwards, right? Some finitely many payoffs for now. And they have corresponding probabilities. In other words, that the game ends in a particular state, that particular state gives you a particular payoff. And then the question is, what will happen? What will happen if you play the game many times? What will be your average payoff per game? To make it slightly more precise, let's perhaps do it this way. Suppose that when a fair die is rolled, you win $6 if the number 6 comes up, and you lose $1 if anything else comes up. So this game has only 2 payoffs to state, either +6 or -1, right? So would you like to play this game? Would you have played this game? And if I could simulate playing this game right now 1 million times, would you play it? If I could simulate it being played 6 million times, would you have played it? That's the question here.
Wouldn't you just end up having the same amount of money? Because let's say you lose 5 times in a row.
Yes.
Or no, I guess you would gain. If you lose 5 times in a row, you would lose $5.
Exactly.
But then if you win once, you would gain 6, so you'd have $1.
Yes.
Oh, so I guess I would play?
Well, you say it like an American, like with a question mark, right? So should I get this coffee? Right? Or something like this. My brother makes good imitations. I make terrible ones.
I mean, if the logic I just went through is right, then yes, I would play, but I don't know if the logic I just said was correct.
Yes, we'll consider that again, but great, right? I'm glad that not everything I'm talking about is meaningless. You seem to be pretty good at the subject, my impression. So here is, it says I'm walking back and forth. I don't tend to think in numbers. I tend to think straight away in abstractions, and then I do numbers, right? But other people seem to be somehow differently oriented, right? So here is in the general situation, right? So in general, you would have maybe different winnings. Maybe sometimes you lose more, sometimes you lose less, sometimes you gain more, sometimes you gain less. So something that you do has different payoffs, a payoff x1, x2, all the way to xk. Finitely many payoffs, maybe k is a large type, right? So then how much will you win if you play n games, where n is a huge number? Right? So let's imagine that we played many games. Some of them produced payoff x1. You imagine you have a table of winning. Game 1, what type of payoff? One of those payoffs came out. Game 2, one type of payoffs came up. Right? Game 1 million, one type of payoff came out. And then you take this huge table and you group it like this. Just make the computer or something else identify all the games that produce payoff x1, correct? So n number of games where the payoff was x1. Gather them together. How much did they bring you? They brought you each x1, correct? So together from those games you won x1 times the number of games that produced x1. If it's negative, that's the same. You won negative dollars, that means you lost, right? Make sense? And then do the same for all the games that ended in payoff 2 and all the games that ended in payoff 3, all the way to all the games that ended in payoff k. And here in the numerator, I see the sum of your payoffs, right? This numerator represents your total payoff for all the games. For all you played the billion games, this n is a billion, and this number plus all the way to nk adds up to a billion. But I grouped them and multiplied each by the corresponding, because each of them are produce the same payoff, so I can factor the payoff out. And now I have the number of games corresponding to the payoff multiplied by the payoff. Numerator is clear? Completely, yeah, because yeah, so yesterday people were, most of them were quiet, and those that weren't, like one or two, said they don't understand. So then writing it in sigma notation, this is what I see, correct? Now I can put down the xj and just look at this expression, and I take the limit because n is huge, so I imagine taking the limit. So this quantity, the number of games that produce payoff xj divided by n, by hypothesis, if we say we know the probabilities are available to us, then we would expect this to be the probability, right? It's really that limit. Nature will really show its preference as this ratio, right? So let's say if the preference for a particular payoff is 1/6, so basically once you play 6 million games, you think that about 1 million of them produced payoff xj, if that's one. Right? So and the bigger the number of games, the more this observation is true. That's kind of my understanding, intuitive understanding of what probability is, right? Is that maybe because nature has that preference and you know it ahead of time, so then if you simulate with many experiments, that preference will be pronounced. Clear? So that's why I'm saying this part is equal to xj p xj. Does it make sense? So it's a summation of xj times pxj. If n is large, then this quantity is kind of like pxj, and in the limit it's exactly pxj. So this is the abstract part, extremely important. Am I clear to you?
I think so. So when you're saying, is it n of x equals xj, or is it?
Yeah. So this
n
notation,
times...
there's no times, right? This in parentheses means count the number of games that produced x1.
So that n is not necessarily the same as the n in the denominator,
Has
or
nothing
it
to do with
is?
it. Or there's summation. So here is what's true about them, right? If I look at this and this and this, what do they add up to?
They would add up to that.
Exactly.
To 1. So
to
or
n,
to that n.
to n, they will add up to n. Perhaps if you would prefer, I can pretend that I'm doing a simulation. Would you like that? I'll show you how that works. So yeah, so let's say that this is what's happening. You can see the whiteboard, yes? So let's suppose that we have that game where we had $6 if 6 on die, and minus $1 if anything else on die. So then imagine you have this table. And it will go on, right? I'm just drawing, let's say, only a few possibilities. So this is game 1, game 2, game 3, game 4, right? So let's say that what happened is that the outcome for game 1 was -1. The outcome for game 2 was -1. The outcome for game 3 was actually 6. For 4, -1. And let me maybe draw a little bit more. So we have also 5, 6, 7, 8, right? And then what we have is maybe for 5 it was again -1, for 6 -1, for 7 -1, for 8 also -1, right? And yeah, so let's actually add up also 9, just to have more of them, right? So let's say 9 and 10, right? So for 10 it was -1, but for 9 it was 6. Okay, so this is you played 10 games, right? Not many enough, but 10 games. So then what is so we have here n of x equal to -1. What's the number? The number is, what I do, I just tally all the -1s, right? So I look here, it's 1, it's 2, it's 3, 4, 5, 6, 7, and 8, right? So this is simply 8. Good. And the tally where x equals to 6 happens to be 2. They add up to 10, right? Because all the states that could occur must add up to 2. Now, how much money did I earn, right? I could have said -1 plus -1 plus 6 plus -1, or I could have added up the -1 separately and the 6 separately, right? So how much money I earned? I earned -1 times the number where x produced -1, which is -1 times 8. And I also had 6, and x equal to 6, right? Which was 6 times 2. So what I earned in total is -1 times 8 plus 6 times 2. That's what that is saying. It's just I'm tallying it, right? And then the question is, how much do I earn per game?
I guess you would then divide
Yes.
4 by 10.
Yes, I'll basically divide by 10, everything by 10, right? So I can then divide, and I can also multiply by the payoff and divide the number of outcomes of payoff -1 by 10, and the number of outcomes of payoff 6 by 10 in this case, right? And that will, but 10, of course, it's not very significant. The idea is in the limit, as n is very large, this ratio will be significant because it is the probability. Remember, back to the idea of probability is how many times does some outcome occur divided by total number of trials. And we believe that if you do this experiment many times, you see a convergence pattern. That's convergence pattern is probability. It's unpredictable on any trial, but because nature will show its preference over many iterates, many trials, you will see the number. So that's why we get this definition: xj times p of xj. Clear? That's how. I'm trying to explain why expected value is defined as this summation of payoffs multiplied by the probabilities. Okay, so the expected value of x, where it has in general, right, when we can take even infinitely many outcomes, will be defined as the summation, this infinite series where j is 1 to infinity of xj p of xj. In other words, add up the product of payoffs times probabilities. That's the weighted average there. Or in general, it's x times p of x, where we don't really need to bother with probabilities that are 0. Just add up the probabilities that aren't 0. So that's another way of writing it out. Does it make sense? So for example, if x is the outcome when you roll a fair die, the expected value of x is 1 times 1 over 6, because imagine that you have payoff, right? So if you roll, this is a different game, you roll a die and the payoff is $1 if it comes up 1, $2 if it comes up 2, $3 if it comes up 3, and so on, right? So how much will you be getting per game on average, right? Obviously, you roll it once, you get maybe $1. Another time it will be $3, right? But on average per game, if you play it many times, many ends, right? So what you will see is that the number of outcomes where the die came out 1 divided by total number of games will approach 1/6. Make sense? So basically we have 1 multiplied by the number of outcomes in my simulations that produced 1, 2 multiplied by the number of outcomes of the simulation produced 1, and then I divided everything by the number of simulations and distributed. So then the number of simulations that produced 1 divided by total number of trials will converge to 1/6, and similarly for everything else. So that's how I get the summation. Make sense? It's this n that I distribute here, 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 everywhere, right? I distribute this n and make into fractions, and then the ratio of this ratio, for example, to that, this ratio will simply be approaching, the number p x1, the weight of x1. Make sense? Great. So that's the definition of expected value. And for the expected value where I roll fair die, the number is going to be 1 plus 2 plus 3 plus 4 plus all the way to 6. I forgot to write plus 6 here, I think, right? Plus 6 times 1/6. That will be 1/6 summation of all the k's, which will be easily, right? It's the same thing as 6 times 7/2. That's summation of k. You can see it in 2 ways, right? I think, well, you know why, right? I don't need to explain. So so then what I can do is I can cross out the 6. So the answer is 7/2. It means that if you play it many times, the game is the same as if you would be getting per each game $7/2 in this particular simulation, right? Or again, I'm not sure. So you understand. So the number that comes out is on average 7/2. So if you kind of average all the numbers that were coming out, you will see that if you actually run the experiment of rolling the die and you produced a very long table and you want to know what's the average of the table, it will be very close to 7/2 if the number of games is large. Let's say 1,000,000, it will be very close, right? By the time you have 10,000 simulations, it's already going to be very close, but by 1,000,000, it's going to be very close. Make sense? So if you have a table with 1,000,000 entries and you see what are the outcomes on the die, you average them, you will see 7/2. That's what this is saying. Okay, so then in this game, what happens if you play 1,000,000 games, right? How much money are you spending to win? Why if I could simulate it right now, everybody would be happy. If I could even do it in a year, it would be. If I could play, simulate playing those 1,000,000 games a year, it's really a great salary, because it will be, what's the expected value? The expected value will be, let's call this variable y, it's either -1 or 6. So it's -1 times 5/6 plus 6 times 1/6, or on average per game you get 1/6 of dollar. That's per game, you see. So if you play 1,000,000 games, it's as if you got 1/6 of a dollar per game, or in total you got 1,000,000 divided by 6. So if you play 6,000,000 games, even better, you get $1,000,000, right? With almost certainty, you understand? So you play this, it will be virtually certain that's the amount you get, and the more games you play, the more certain is the amount that you get. Make sense? That's the idea. So here is another example, slightly more complicated one, right? And see if you can figure it intuitively, and then we can try to do the calculation. So a game of Russian roulette is played with a revolver having 7 chambers. How many rounds do we expect the game to last? You see, so how does it work? You roll the drum, and then you press the trigger, click. Never did not fire. Somebody rolls the drum again, you hear click, right? So, and at some moment you will hear the shot. So on average, how many games do you think how many rounds will the Russian roulette last? Each of them again, right? So you don't consider pressing after, you always roll the drum first before you press, because your chances of being shot at each round is 1 out of 7.
So I mean, for 6 out of the 7 rounds, you're fine. And then for 1/7, you are not. So is 1 round you pull the trigger once, or is that you? I mean,
Yeah,
yeah, I
you
guess
pull
so.
the trigger once. Every time you hear a click, that's 1 round.
Okay.
So click, roll the drum, click, roll the drum, right? I'm not asking who is going to win. I'm asking only, about the drums, right? We can ask interesting questions about it. The first person who begins, does he have an advantage or a disadvantage, right? Or maybe it's equal. Doesn't matter who begins first. But that's a different question, right? We can consider that. Later.
So I guess it would just be, I mean, 1 out of, so every 7 rounds, someone could be less, but maybe at least 1 out of every 7.
Yeah, so you would see the expected number of games is
7.
yes, you have a very great intuition. Amazing, right? Exactly 7, right? So it doesn't mean that the game will last 7 rounds. It will last. There is variance. There is all sorts of other things. It's unpredictable how many rounds it lasts. But if you played many games, in other words, you simulated playing millions of games and you recorded how long did they last, right? So one game lasted 24 rounds, another game lasted only 1 round, right? You have all sorts of different possibilities, but you average all the number of times that the game lasted, and you find that the average is 7. You understand? So we have to really be clear about what we mean by average, right? What I imagine is a long table and listing the, let's say, first game, that's how long it lasted, how many rounds second, how many rounds, and maybe if I have millions of games, right, then how many rounds each of them lasted. And I find that in this giant table, the average will be 7, as you predicted without doing any calculations, which is very good. Many people do not, are not able to do it. Right, so here is mathematically why. Okay, 7 rounds long. So we first understand what's the probability that the game lasts n rounds. It means that the gun did not fire the first n-1 rounds and fired on the last round, right? And the corresponding expected value is n multiplied by its probability. Does it make sense why? Because when I add up the table, what I really do is I actually imagine adding up all the, not through the table, but I actually imagining cutting out all the outcomes that ended up in round 1, all the outcomes in round 2, and doing the summation for them separately and multiplying them by the corresponding number, right? Because you see, so this game was n rounds. I'm averaging the round, right? So I'm averaging those numbers. So they're going to be n of nx equal to 1 times 1. That's going to be the same quantity. That makes sense? Yes, I'm seeing it, and I'm hoping you see the same table I do, because I'm not sure if I'm translating in words well enough what I'm seeing. Well enough? It's like what we did before with the payoffs of 6, same thing, right? Just I separated, right? So that's where the n comes from here, because we have to be really, really clear about what is this number, what is the meaning of this number. So that's again, when I look at this thing, I hear something like, I think they said bow bow, but I was hearing pow pow, right? So I see this formula and I remember Deer Hunter, pow pow. So this is the summation, and without doing any effort, you right away realize the answer is 7. You see how nice it is in probability? If you have intuition, you see that this semi-complicated summation is right away 7. But let's verify it. How do we sum such a thing without having an intuition for what it will equal to? So first, we know the geometric series of the form x to the n-1, where n is from 1 to infinity. It's this thing, and we can use this fractal thing, right? The fractal idea is that within the formula, I see the same formula. So if this is g, 1 plus, I factor all bx, it's going to be g is equal to 1 plus x times g. You'll see that, right? It's because I look starting from this x, I put parentheses, and I can factor out the x, and what I will see in parentheses is g itself. So it's 1 plus x times g, which makes g equal to 1 over 1 minus x. Good? Now, I want to know how to sum this h, in other words, where it's n times x to the n-1. Because you see here I have this 1/7 I can factor out. I just essentially have problem summing this x to the n minus 1 times n. Right? There are all sorts of ways to do that, but here is one very simple. I can write n as n minus 1 plus 1 and distribute the x to the n minus 1 into here and here. Yes? So it's n minus 1 x to the n minus 1 plus x to the n minus 1. So far good? And then I can sum x to the n minus 1 separately. It gives me 1 over 1 minus x, because that's just the G summation, just a regular geometric series. And I'm left with a summation that somewhat looks like what I had before. I can label n minus 1. I can call it m. So here it's m equal to 0 to infinity of m times x to the m. Here it is. And then, of course, the 0 term I can drop. I don't really care about. So it's like m equal 1 to infinity, m x to the m. Good? Which is what? Which is if I factor out x, this is exactly h. So h is equal to x times h plus 1 over 1 minus x. So you're with me, yes? Everything I said, I'm not sure how easy it is to follow. So then I move it across and I see that 1 minus x times h is 1 over 1 minus x. And so h is 1 over 1 minus x squared. And so the expected value is accordingly 1 over 1 minus 6 over 7 squared times 1 over 7, because in this formula I haven't multiplied the 1 over 7 just yet. Multiplying it by 1 over 7, what happens here, right? So this is here, it's simply 1 over 7 squared times 7. So that's 1 over 1 over 7. And as you predicted, the answer is 7. So on average, it will be 7. Now, is the average significant? That's a difficult story, right? I mean, because what does it signify, right? It's just that you averaged all those columns. On average, it will be this number, sometimes more, sometimes less. Then if you have variance, as we talk about other things, then you can kind of sense of how likely it's going to be near 7 or more than 7, right? How far away from the average will typical scores be jumping around. It's just like giving a summary of how the numbers jump around. Right? So you can use such things, I suppose, to estimate when those annoying football games are over, and you can then watch 60 minutes. Even 60 minutes are also annoying, but you get older, you watch 60 minutes. You know what it is? Yeah. Sounds good. So that you see how quickly we went through it. Less than an hour. It took me longer. Takes me much longer when I do. Maybe I should just do all the recordings with you. We can cover it twice. All right. So any questions?
Not on this stuff. No, I don't think so. I guess the one thing I got lost at, I got most of it until you got to h equals 1 over 1 minus x squared. I lost where the squared comes from.
Let's walk over this. Let's do this calculation. If you afterwards you have some questions regarding the exam, we can go over that too. Okay, so let's see. Here is the idea. So we are trying to calculate this h, right? H equals to the summation. It's annoying to not write the summation here. The summation where n starts at 1 to infinity of n x to the n minus 1, yes? So what can I do with this n? I look at this n and I think, I want to create an iteration process. So I'll write it as n minus 1 plus 1. Yes? And then I distribute the x to the n minus 1 and to the 1. I don't, so I distribute the x. And what do I get? I get agreed? Yes? And what is that? This is simply So you see, look at it, right? So, what is the summation? The summation is just a geometric series. I right away know the answer. For this one, it's simply 1 over 1 minus x. If you need a review of that, I can again show you how I know it, right? And then what about this guy? Well, I can relabel. I can say that this thing here is m. Why do I relabel? Because I want to make it look like h. I'm trying to find h within itself. That is m, yes? And so what I see is that h is equal to the summation. If I relabeled it into m, it's the same as summing from m equal to 0 to infinity of m x to the m plus 1 over 1 minus x. So far good? Now there is no reason to add m equal to 0 because it's just it's multiplied by 0. So it's really, we can skip it, right? We might as well say here 1. So that looks like h. Look at it. Except I don't have a minus 1 here, right? So what I do is I put a minus 1 and I factor out the x. So now what I see in the summation is just h. So now I see h equal to xh plus 1 over 1 minus x. Moving it across, I have 1 minus x times h equal 1 over 1 minus x.
Okay,
Which
yeah, I
means
see it
h equals, you can do it other ways, but that's very quick and simple.
Yeah. Okay, yeah, I get it now.
Good, wonderful. Good, and then we have 1 over 1 minus x squared.
Okay, yeah.
Good. So if you want to ask me anything else.
I think I'm pretty good. I guess, I mean, I don't know how much you can tell me with this, but for number 6.
1 second, I'll then stop this video.